Hi, Assalamualaikum and a very good morning. So now we are in chapter 2, atomic structure. And now we're going to focus on the subtopic of 2.3, electronic configuration, part 1 of the video. So in this video, we're going to learn about the Aufbau Principle, Hunds Rule and Pauli Exclusion Principle. Also, we're going to apply all the rules that we have learned in part A, and this is used in order to fill the electron into atomic orbital. Next, we're going to learn on how to write the electronic configuration of an atoms or the monoatomic ion using the spdf notation. So the learning outcome of A, B, and C will be covered in part 1, which is in this video. For the learning outcome of D, we're going to look about that in part 2 of the video, which is in the next video. So without any further ado, let's start with part 1 of the video first. So representing electronic configuration. So the electronic configuration basically showed us of how electrons can be filled in the orbital, and it also described the arrangement of electrons in an atom, whether it is full fill or half fill. And the electronic configuration of an atom or monoatomic ion can be represented by using two methods. First method is by using the orbital diagram, and the second method is to use the spdf notation. So now let us look into the orbital diagram first. So for orbital diagram, so each orbital can be represented by a box, a platform, or by a concentric circle. Okay, so either one of these, and each electron is represented by an arrow. And this arrowhead indicates the direction of spin, because you know that your S here, which is the electron spin, can be plus half or minus half. And to make your life easier, you can assume that your plus half here going to be going upwards and your negative half here going to be downwards. Okay, so it is basically up to you. You can also say that plus half going to be downward, but to make your life easier, I think it's better for you to just assume that the plus half going to be upwards and the negative represent the downward part. All right. And for one single arrow here, it represents one electron. And for a half and another half arrow here representing two electrons. Okay, so let us look into the example here, which is oxygen, which has 8 protons. So in a neutral state, 8 proton will have 8 electrons as well. So we can arrange the 8 electron into the orbital diagram. So we know that we have 1s, 2s, and 2p, and 1s have one orbital, which is s orbital, and it can fill 2 electrons. So 1s2, 2s2, 2p4. And this is first way you can represent that in which is in the box. And you can also repeat the same process, which is 1s, 2s, and 2p. So you know that with 8 electron, the 2 electron will go to 1s2, and then you have 2s2, and then we have 2p4. Okay, and we're going to learn on how to fill in the 8 electron in the later slide. Okay, and because we have 8 electrons, so going to be 2 here, and 4 here, which is in the terms of platform. Just now in terms of boxes. And the other way that you can present it is in terms of concentric circle. Okay, so basically the same thing, but it just you make circle for the electron. And the most popular one is basically box and platform. And in order to do the orbital diagram, the labeling here, which is the green color, is compulsory to be written. Without the labeling, then your answer will be wrong. Alright? And the second method is to use the spdf notation. So the spdf notation means we need to write the symbol for the occupied subshell and adding a superscript to indicate the number of the electron in that subshell. So let's say if we have our subshell here, which is 1s, and then we need to add a number to represent the number of electrons in that subshell. Okay, for example, we're going to use the same example as before, which is oxygen, which has 8 electrons. So the 8 electron here, 2 electrons will go to 1s orbital, and then the 2s orbital will have 2, and and then the 2p orbital will carry 4 electrons. Because you know that when n is equal to 1, L is equal to 0. So you can only have one S. But when n is equal to 2, L can equal to 0, which is 2S. And then when n equal to 2, L is equal to 1, which is 2p. Okay? And you know that when L equal to 0, M is equal to 0. So you can only have one orbital, which is 2s. And this orbital can fill 2 electrons. Meanwhile, for here, you know that 2 n equal to 2, L equal to 1 is 2p. And then when you find the m value, you can get 3, which is negative 1, 0, and plus 1. So that is why you can get px, py, and pz orbital. So 2 electron going to enter here, 2 electron going to enter here, and 2 electron going to enter here. So the total going to be 6 electron if it is full. Okay, but now because we only have 8 electrons, so going to be 2, 2, 4. All right. And the 2 here representing a principal quantum number, which is the energy. The P here representing an angular momentum quantum number, which is L, which is equal to 1 as I shown just now. And then the number, which is the superscript here, will represent a number of electrons in the subshell. All right, so this is the SPDF notation. And for assigning electron to the orbital, we need to obey these 3 rules. So the first rule is the Aufbau Principle. Second is the Pauli Exclusion Principle. And the third rule is the Hunds Rule. Okay, and as before, I have mentioned we're going to use the similar concept that we have learned in quantum numbers. So you know that 1s, which is n equal to 1, L equal to 0, will have a subshell of 1s, and hence the number of orbital which depends on m will have 1 digit. So going to be 1 here, and the number of electron going to be 2. So for 1s, the maximum number that it can fill is 2 electron here. Okay, and meanwhile for 2, it has 2s. So 2s can fill 2 electrons. And then 2p can fill 6 electron maximum. Okay, so we have 10 electron, right? And then for 3s2, you know that you can fill the maximum of 2 electron as well. Okay, and so on and so forth. Alright, so now let us look into the principle here again. So the Aufbau Principle. So according to Aufbau Principle, the orbital of the lower energy need to be filled in first with electron, and only then the orbital of high energy are filled. So the order of filling the orbital will follow the sequence, which is we need to fill 1s first, followed by 2s, followed by 2p, and then 3s, 3p, 4s, 3d, 4p, and 5s. Okay, so this is the sequence of we filling it in. And this is gotten from your quantum number itself, because you know that n is equal to 1, then L is equal to 0. So you have your 1s here. And then similarly, when n equal to 2, L can be 0 and L can be 1, which is 2s and 2p. And then here, n equal to 3, L can be 0, which is 3s, L can be 1, which is 3p, and then L can be 2, which is 3d, and so on and so forth. You get the idea, right? Okay, so the idea of filling in the orbital needs to go from the lowest energy, which is 1s. Okay, because n is the lowest and 5 going to be the highest. Okay, and the way that we're going to fill it in, you just follow the arrow here. Okay, so this is the way that you can memorize it, which is 1s, 2s, 2p, 3s, 3p, 3d, and then 4 become 4s, 5s, and then lastly we're going to have 5g here. But usually for our syllabus, we don't have until like that. Okay, so the way that you're going to fill it in, you just put an arrow, it passes through the number. So the first orbital that we're going to fill in is 1s, followed by 2p, followed by 2p, and then 3s. Okay, and then you just draw an arrow here again, 3p, 4s, and then 3d, 4p, 5s, and then so on and so forth. Okay, so this is how we're going to fill the electron. So that is why when you look into the earlier example, you have 1s, 2s, and 2p, where the 2p here will have px, py, and pz. Okay, and this can fill 2 electrons in each orbital. Okay, so the way that we're going to fill in the electron, for example, if we have 5 electrons, okay, you might think that we can fill it like this, like this, like this, like this, and like this. Okay, so this is not entirely true. Instead, we're going to use the below part here. So when you have 5 electrons, you need to fill in the lowest energy level first, which is 1 and 2. And then you're going to have balance of 3, right? Because 5 minus 2 will have 3. And then you need to fill in the next one, which is half and positive half, because the electron spin need to be in opposite direction, plus half and negative half. And then the balance one here will have up here. So total of 5 electrons. Okay, so this one is the incorrect one, and this one is the correct one, because we need to fill in the lower energy field. Okay, the lower energy need to be filled in first, and it need to be filled completely with positive half and negative half. So this one is the wrong one. Okay, moving on to the next principle, which is Pauli Exclusion Principle. So according to Pauli Exclusion Principle, it stated that no two electrons in an atom can have the same 4 quantum number, which is N, L, M, and S. So let's say if we have one s orbital here, and now you have 3 orbital in the orbit. You have 3 electron in the orbital. So if you were to find out the quantum numbers for A, which is the NLMS, you're going to know that your N here going to be 1, because N equal to 1. And then because it is an S orbital, so your L going to be 0. When L equal to 0, then your M going to be 0 as well. And then because it points upward, so you're going to say that it is plus half. Okay. And how about B? So for the B part, it's going to follow the similar one, which is 1, 0, 0. But because it goes into the downwards direction, so it's going to be negative half. And now for C, we're going to have 1, 0, 0. And then it points the same as A. Okay, which is plus half. Okay, and you know that this one is wrong because in the orbital, only 2 electrons can fit in the orbital. Okay, because when you have 3, your quantum number will be the same, and either one of those going to be wrong. So for in this case, C is the wrong one. Okay, because we cannot have the same 4 quantum numbers. All right, one need to go upwards and the other downwards, and in each orbital they're going to be 2 electrons. Okay, so for this one is also considered wrong because both things pointed upwards. So this one is wrong. Here is correct because one upwards and one downwards, and here is wrong because on the same orbital, both of the electron pointing downwards. All right. So now for Hunds rule. Hunds rule stated that when electrons are placed in a set of orbitals with equal energies, or known as the degenerate orbital, the electron must occupy them singly with parallel spin first before they occupy the orbital in pair. So what is this statement trying to say? That let's say if we have 2p orbital, so you know that the 2p orbital will have px, py, and pz. So these 3 orbital of 2p has equal energy. So let's say if you have 4 electrons to fill in here, so what you need to do is you need to pair them you have to fill in 1, 1, and 1, because it needs to be occupied singly with parallel spin. So you can go upwards, upwards, and upwards, or you can even go downwards, 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 because it needs to be filled singly and then with parallel spin. So they are both singly and parallel spin. And the balance of 1, then only you pair them. the balance of 1, then only you pair them. So both way are accepted. Okay, and this one is the wrong one. Okay, so if you put both like this, then automatically this is going to be wrong. If you put it like this, also wrong, because you need to fill in singly first, one by one. Okay, and this one is also wrong because this is not parallel. It filled singly, but then different direction. And for this one is the correct one because it pairs singly, and then only they pair. All right. To understand more about that, let us look into the example. So now, writing the electronic configuration, we need to write the electronic configuration for this species here using orbital diagram and in spdf notation for the following atoms and ion. So here we have carbon. Okay, so carbon will have 6 electrons. So for me, I would love to start with spdf notation first. So you know that I need to fill in with 1s orbital first, followed by 2s, 2p, 3s, 3p, 4s, and 3d here. Alright, so you need to remember the Aufbau principle. Okay, so fill in this one first, followed by this one, this one, this one, and this one. Okay, you can refer back to the previous slide. So for carbon, they have 6 electrons. So when they have 6 electrons, I know that my electronic configuration is going to be 1s2 because s orbital can fill 2 electrons. And then I'm going to move on to the next part, which is 2s, which can also fill 2 electrons. And then I'm going to move on to the next one, which is 2p. Okay, and I have used up 4. Now the balance here is 2. So I'm going to have my SPDF notation here going to be 1s2, 2s2, 2p, 2. And now I'm going to draw the orbital diagram, and I will love to use the platform method. Okay, because they have 3 methods, right? The boxes, the platform, and concentric circle. So I'm going to use the platform. So 1s going to have 1 orbital, 2s 1 orbital, 2p will have 3 orbital here. So what I'm going to do here, I'm going to use the Aufbau principle, which is I'm going to fill in the lower energy level first, and then I'm going to the next 2s orbital. Okay, and then the 2p orbital I need to fill in singly. So it's going to be looking something like this. So all the concept of Aufbau, Hunds Rule, and Pauli Exclusion principle need to be applied when we are filling in the electronic configuration. So now let us do B, which is 7, nitrogen 7. So here is the proton number, but when it is neutral, the number of proton and electron going to be the same. So the electronic configuration here going to be 1s2, 2s2, and then the balance here going to have 3. Okay, so 2 plus 2 plus 3 going to have 7. Okay, so as usual, we're going to do, this is the SPDF notation here, and now we're going to do the orbital diagram, which is the platform method as well. So 1s2, 2s, and 2p. Okay, so for 1s, I have 2 electrons, so going to be up and down. For 2s, plus half minus half, and then 2p3. And according to Hunds rule, I need to fill in singly first with parallel spin. Okay, so you cannot write it like this. So this one is wrong, or you cannot write this like this. So this one is also wrong. Okay, so this is the accepted one. All right, now you can try for sulfur. So sulfur will have 16 electrons. So you can start with SPDF notation first, which is 1s2, 2s2, 2p6. So we have used up 10. And then next, we're going to use the 3s orbital, which have 2, total 12. And then 3p can fit maximum 6, but now we only have 4. So we're going to be 4. So total is 16. So similarly as before, use the orbital diagram and then fill in the 16 orbital. 1, 2, 3, 4, and then fill in singly 5, 6, 7, 8, 9, 10. Okay, so need to completely fill, then only you move on to the next orbital, which is 1, 2, already 12, and then another 4. Fill in singly first, 1, 2, 3, and then you pair them. Alright, nice one. Now fluorine minus. So for the fluorine, you know that it has 9 proton number, and hence it's going to have 9 electron. But now, because it have a negative charge, it means that it will receive another electron. So the total number of electron going to be 10 electron. So the SPDF notation here going to be 1s2, 2s2, 2p6. So enough, all 10. So similarly as before, use the orbital diagram, which is 1s, 2s, and 2p. So 1, 2, move on to the next one, 3, 4, and then here, pair it singly first, and then only pair it. Okay, right? So it has 10 electrons in total. And as what you can see, when you write the orbital diagram, you don't have to write the electron here because it has been written up here. For SPDF notation, you need to write the electron. But for orbital diagram, you just write it as the subshell. You don't have to write the number of electron here. Okay? Now we move on to example number 2. So for example number 2, we need to draw electron in boxes diagram, which is orbital diagram, for the electronic configuration of titanium, which has a proton number of 22. And then we need to write the SPDF electronic configuration for titanium and titanium 2 plus ion. Okay, so for titanium, you have 22 electrons. And similarly as before, to make your life easy, I would suggest to start with SPDF notation first, which is 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, and then 3d2. So you need to follow Aufbau Principle. Follow the sequence. Okay? And now when you are needed to draw the orbital diagram, which is electron in boxes. So you're going to draw the boxes, follow the sequence here, and then you need to fill in the electron here. So 1s2, 1 and 2, 1 and 2, and then you have 2p6, 1, 2, 3, sorry. We need to fill in what singly first, then only it is being paired, and then 1 and 2, 1, 2, 3, 4, 5, 6. So we have 18 electron in total. Okay, 18, and then we have 4s2, 1 and 2, and then 3d we have 2 electrons, so it's gonna be 1 here and 1 here. Okay, so this is how you write the electron in boxes diagram for titanium. And now we need to write for titanium and titanium 2 plus. So titanium is already here, but now we need to focus on titanium 2 plus. Okay, so titanium is something that I have shown just now. For titanium 2 plus, now is a little bit rare. Okay, so we need to donate electron. So how much should we donate? Because it is 2 plus, so it's going to be donating 2 electron. But we cannot remove the electron from the 3d2 orbital. We need to remove it from 4s2 because n here is equal to 4, which is the highest. So we need to remove the electron from the 4s2 orbital. Okay, so when we remove 2 electrons, so it's going to become 3p6, 3d2. Okay, so basically, when you're removing it, you need to remove from this part here. Alright. However, this is only applicable when it involves 4s and 3d. Okay, But for a normal one, for example, sodium, okay, so sodium you have 11, so you're going to be 1s2, 2s2, 2p6, 3s1, right? So if you want to make Na plus, you remove it from here because n is equal to 3, which is the highest. So you remove 1 from here, and then you're going to be 1s2, 2s2, 2p6. Okay, but from here, yeah, we need to remove from n equal to 4, which is the highest, but it is from the middle. Okay, so I think that's all for today's video. See you again some other time. Bye.